In this example, we want to find solutions to the initial value problem dy dx equals 3x squared plus 4x plus 2 over 2y minus 2, with the initial condition that y of 0 is negative 1. To see that this is a separable differential equation, we'll multiply both sides by 2y minus 2 to get 2y minus 2 times dy dx is equal to 3x squared plus 4x plus 2. Now that we have it in this form, we can integrate both sides with respect to x. So on the right, we have the integral of 3x squared plus 4x plus 2 dx, while on the left, we have to use the substitution rule to get the integral of 2y minus 2 times dy. Now, each of these integrals we can compute on their own. On the right, the integral of 3x squared is x cubed, plus the integral of 4x, which is 2x squared, plus the integral of 2, which is 2x, plus some c, that's the constant of integration. While on the left, we have the integral of 2y is y squared, minus the integral of 2, which is 2y. As I've said before, we should have a plus c on the left-hand side as well, but we'll clump it all together with the constant of integration that's on the right. And with this, we can conclude that the solutions y satisfy the equation y squared minus 2y is equal to x cubed plus 2x squared plus 2x plus c. So we've found the implicit solutions to the differential equation. And now using the initial condition, y of 0 is negative 1, we have negative 1 squared minus 2 times negative 1, plugging in y equals negative 1 on the left-hand side, is equal to 0 cubed plus 2 times 0 squared plus 2 times 0 plus c, plugging in the value of x, which is 0 at our initial condition. The left-hand side is negative 1 squared plus 2 is 3, while the right-hand side simplifies to just c. So we get that c equals 3, and we can conclude that y can be found implicitly as y squared minus 2y is equal to x cubed plus 2x squared plus 2x plus 3. We can take this solution a little further though. Notice here that we have a quadratic equation in y that we can write as y squared minus 2y minus the constant with respect to y, x cubed plus 2x squared plus 2x plus 3 equals 0. And writing it in this form, we can use the quadratic equation to solve for y explicitly. In particular, using the quadratic equation, we get that y is equal to negative 2 plus or minus the square root of negative 2 squared minus 4 times 1 times the negative of x cubed plus 2x squared plus 2x plus 3 all over 2. And while it's a little bit messy, we can clean it up a bit. If we simplify under the square root by doing negative 2 squared and factoring out the 4, we'll have 2 plus or minus the square root of 4 times 1 plus x cubed plus 2x squared plus 2x plus 3 all over 2. And bringing the 4 outside of the square root, as the square root of 4 equals 2, we'll have 2 plus or minus 2 times the square root of x cubed plus 2x squared plus 2x plus 4 all over 2. And when we do that division by 2, we'll be left with 1 plus or minus the square root of x cubed plus 2x squared plus 2x plus 4. But remember, we have an initial condition that y of 0 is equal to negative 1. And only one of these satisfies that initial condition, which is y equals 1 minus the square root of x cubed plus 2x squared plus 2x plus 4. You can check this by plugging in x equals 0 and verifying that y equals negative 1 here. While we had to go through some tedious algebra to get here, we now have an explicit solution of y to our differential equation. y equals 1 minus the square root of x cubed plus 2x squared plus 2x plus 4. And it's preferable to solve our separable differential equation explicitly for y if we can. However, I want to add that it's rare that we can find explicit solutions to separable differential equations. So we often need to leave the solutions of y implicitly defined, as we did in the last example. Again, we can get most information that we want in both the explicit and implicit forms, though it's easier to work with if we can solve for y explicitly, as we did here.